I'm going to find out. All right, we're recording now. So I had a number of people request problems via email. And so I want to look at some things from the last lesson. This is the lesson we're heading for today. Lesson 2.4, continuity and one-sided limits. So from exercises from last time, we had, here's a fairly easy one, number 35, where you want to take a limit as x approaches 1. You try substituting in a 1, and it works. You know, you substitute in a 1, you got the natural log of 3 times 1 plus e to the first. Welcome, Jordan. And substitution just works just fine on that problem. One that was requested of me is number 61. So let's take a look at that one. Okay, in black is number 61. Find the limit as x approaches 0 of 1 over 3 plus x minus 1/3. And all over x. And of course, you cannot substitute here. Okay, I got a... Hi, Keenan. Okay, Keenan's muted now, and Jordan will mute him. All right. So, anyway, this is number 61 in black. You can't substitute, so you've got to come up with some way to get that x on the denominator to cancel. And the way to do it is, well, just get a good old common denominator on top so you can bring that together, and then maybe something can happen. So the common denominator is what? 3 times the quantity 3 plus x, just the product of the two denominators. So in the first denominator, I need to provide a 3. So I multiply top and bottom by 3. That's the same as multiplying by 1. In the second fraction, I have to get a 3 plus x in there, so I multiply the top and the bottom of that fraction by 3 plus x. That creates now a common denominator of, over here, 3 times 3 plus x. And on the top, you get a 3 from the first fraction, and then you get minus the quantity 3 plus x for the numerator. And then that's all still divided by x. All right. So the numerator, welcome, Maria. The numerator, you can simplify 3 minus, you're subtracting 3 and you're subtracting x. All right. And then what is 3 minus 3? Okay, that's gone, and you still have your minus x. Okay. We got to do some muting here. Okay, we're back. So, so what happens on top is the 3's wipe out, you have a minus x. On the bottom, of course, when you divide all of this by x, it's the same as dividing by x over 1, which is times 1 over x. And so this x wound up right here, where, let me get my pointer here. So that x winds up right there in the denominator. All right. So anyway, now we can cancel the x's. And you have a -1 left on top and on the bottom. Now we can substitute. When x is 0, you get a 9 on the bottom, and your limit would be -1/9. Does anybody have a question on number 61? Let's also take a look at number 63. So 63 they asked us to find the limit as delta x approaches 0 of this thing. And, well, you can do a little algebra and multiply out that distributive property on the top. 2 times x plus 2 times delta x minus 2x. Now the 2x's wipe each other out, and you have 2 delta x over delta x. And I might have smeared that out a little bit, but over here in the end, you can cancel the delta x's, and you've got your limit comes down to 2. Any questions on number 63? Let's take a look at number 65. The problem is just as it is in the book on the very top there. This time delta x approaches 0 in our limit, and of course we cannot substitute. But we certainly can, what? Simplify the top. And maybe, just maybe, that delta x will have something to cancel with. And so when you multiply out this x plus delta x squared, remember that middle term. Here you got negative 2 times x plus delta x. And then you're subtracting this quantity x squared minus 2x plus 1. So a bunch of things wipe themselves out. X squared wipes out with a minus x squared, negative 2x, and a plus 2x. 1 and a negative 1, leaving you with this term right down here. And we're still stuck. You still can't substitute a 0 for delta x. But there is a delta x in every term of the top. You can now factor it out. And then, yes, we can cancel the delta x. Now, can you substitute in this 2x plus delta x minus 2? Yes, you can. If that becomes 0, your limit would just be 2x minus 2. All right, anybody have a question on that one? Let's take a look at number 77. Now, this one is kind of tricky. So for this one, yeah, the problem was just 1 minus e to the negative x over e to the x minus 1. So this part over here was not, I mean, that's me taking a step. And the x approaches 0, we have a problem, because if x approaches 0, e to the 0 power is 1, and 1 minus 1 is 0, so we cannot substitute. Yeah, well, I multiplied both top and bottom by e to the negative x. The reason I did that, yeah, that's an interesting one, because what happens is on the top you can't do anything, but on the bottom, what is e to the x? I mean, you can do it, but you don't. We just leave that. On the bottom, what's e to the x times e to the negative x? Keep the base and add the exponents. So you keep the base e, add the exponent 0. E to the 0 is 1. And then when you multiply e to the x times 1, you get negative e to the x. And now, 1 minus e to the x, I can cancel those two quantities. I mean, that whole thing cancels there. And all we have left is e to the negative x. Now, can you substitute in a 0? Yes. And the result is 1. So that one was a bit on the tricky side. So, some questions that anyone would like to add from the 2.3 lesson? Yeah, and I just wanted to make this comment too. I mean, make sure, let me go back to the 2.3 lesson. part of the assignment was these true false at the end here, 121 through 126. You need make sure you do those and that you get them. So for example, number 124, let's take a look at that one. So what's the limit? Well, first of all, they're telling you the limit of f of x as x approaches c is L. Now, is it mandatory that f of c be L? If the graph was continuous, that would have to happen. But for example, we could have a graph with a hole in it. And there, f of c does not equal L. But because the two limits on either side still come to the same place, it still has the limit. So this one has to be false. And the point is, you can have a limit where there's a hole, and then f of c would not be L. So anyway, make sure you go through those true false. All right. So today's lesson, continuity and one-sided limits. And we're going to look at some short videos by a site called calculus-help.com, which you might want to take a look at. They will help you with the concept of a limit. Okay. We're going to take a look. Yeah, we're going to take a look at this, and we're going to click on this link. And here comes the first video. What is a limit?
You may have heard a lot of talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit. In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question. And the fact that you don't understand exactly what I'm talking about is because all of the functions you've been dealing with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot. So we might as well review function heights a little bit and then get into exactly what I mean by intending to go to a certain height. Let's start by looking at a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes heights all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2 squared, or 4. This means that the function reaches a height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is the limit as x approaches 2 of f of x equals 4. This just means that whenever I'm getting very close to the x value of 2, my function is getting very close to the height of 4. There's nothing really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take, for example, this function. G of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinates 2, negative 2. The hole exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of negative 2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to negative 2. This begs the question, when exactly does the limit exist? We examine that in the next module.
So, any questions on that video? And Claire, I did see your question. Took me a little while. We will go over number 49. But anybody have a question on that first part? Let's go on to the second part. When does a limit exist?
Now you have some idea of what a limit is, and we need to talk about when does a limit exist. To illustrate my point before we get started, let's set up an example. Let's say you and a friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner, and your friend lives west of the diner, and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side toward some specific value of x. As long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists. Now it's time to get down to the brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually, you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However, if you travel towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We want both. Right-hand limit of f of x as x approaches 4 from the right. And we denote this with a little plus sign in our limit symbol. Our height that we arrive at from the left is called the left-hand limit of f of x as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal. Now let's change this function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrive at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the graph, because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
And next we have, how do you find the limit?
Once you can determine whether or not a limit exists, the next logical step is to try to figure out what the heck that limit is. So that's what we'll be focusing on in this section. How do you find a limit? The fancy word for finding the value of a limit is evaluate. So when you see the directions evaluate, basically you should be expecting to get a numerical answer. There are three major ways to evaluate a limit. They are substitution, factoring, and the conjugate method. We're going to go ahead and start with the easiest one, which is direct substitution. It is just as easy as it sounds. We'll take an example. Here's one. The limit as x approaches 0 of the fraction x squared minus 1 divided by the quantity 2x plus 3. In order to evaluate this limit, all you've got to do is plug in 0 everywhere you see an x. So put in 0 in the numerator and in the denominator, and we end up getting negative 1 divided by 3. So our limit is negative 1/3. It's as easy as that.
Sometimes you really want...
Unfortunately, not all limits are this easy. And you've already seen one for which that's the case. Remember that function that we were dealing with in the first section of this chapter? In case you don't, here it is again. The limit as x approaches 2 of the fraction x squared minus 6x plus 8, all divided by the quantity x minus 2. We looked at this before. It had a hole in it at the coordinate 2, negative 2. And we concluded from that the intended height was negative 2, making it the limit. However, it would be nice to be able to figure out why this is true mathematically. And to do that, we'll have to use the factoring method. As you can see, and as we saw before, direct substitution results in 0 divided by 0, which is not allowed. We'll have to resort to this new method. We'll use the factoring method because the numerator of this fraction is factorable. If we factor it, we'll get x minus 4 times x minus 2. Can you see why that's a good idea? Well, the reason is because now the numerator and the denominator both contain the term x minus 2, which I'm going to cancel out. This leaves the limit as x approaches 2 of x minus 4. This is much simpler to solve because now you can use substitution. And when I do, I get 2 minus 4, which is equal to negative 2. Remember, we knew the limit was going to be negative 2, and we're right. Feels good to be right. If the substitution method fails and the factoring method fails, you're not without hope. You can still try the conjugate method. Before we talk about the conjugate method, though, we might as well figure out what a conjugate is first. Take a look at this expression, the square root of x minus 4. Now, this is a plain old two-term expression. However, it is easy to make the conjugate. All you do is change the negative sign in the middle to a positive sign. The conjugate of the square root of x minus 4 is the square root of x plus 4. That's all there is to it. Now, what if you see an expression like this in a limit problem? For example, this limit problem. The limit as x approaches 16 of the fraction, the square root of x minus 4 divided by the quantity x minus 16. Well, what we'll do is multiply the top and the bottom of the fraction by the conjugate of the radical expression, which, as we said, was the square root of x plus 4. Now, the magic of this is that as you multiply out, the numerator will actually become x minus 16. You don't want to multiply the denominator out. These are not separate factors. Since I have x minus 16 in both the numerator and denominator, I can cancel them, just like I canceled like terms in the factoring method, and I'm left with the limit as x approaches 16 of 1 divided by the square root of x plus 4. Do you see why we didn't want to multiply on the bottom? It makes simplification much easier. Now I'm able to plug in 16. Substitution works. When I do so, I get 1 divided by 8. So the limit as x approaches 16 of my original function is 1/8. And that's the conjugate method. There you have it. There are 3 major methods to evaluating limits. Substitution, which is the easiest. Factoring, which is useful when either the top or the bottom of the fraction is factorable. And the conjugate method, which is useful for radical fractions.
And then just this last one, what makes a function continuous? Which is really what the name of our lesson is today. We're talking about continuity.
Calculus relies heavily upon the existence of what's called continuous functions. In fact, most of your important theorems include a prerequisite that any function in question must be continuous before you could even think about applying the theorem. For example, the intermediate value theorem, which we'll also learn in this chapter, requires that the function be continuous. Well, in theory, continuous functions are predictable functions. They have no undefined points, no breaks, no holes, no jumps in the graph. But enough talk. Let's take a look at some pretty pictures. Now this function f is continuous, but these, g, h, and I, they're not continuous. Each of them, in fact, is discontinuous for a different reason at the x value of x equals c. See, now this one, on g, you've got a little hole in the graph. That's called point discontinuity. Over here on h, you've got a vertical asymptote that breaks the graph. Now this is called infinite discontinuity. And finally here on graph I, you've got a graph that just plain snaps in the middle. And that's called jump discontinuity. Now how can you judge just by looking at the graph of a function if it's continuous or not? Well, a continuous function makes a good bridge. Now see, if I drive across the graph of f, it holds up nicely. Whereas if I try to drive across the graphs of the other functions, I might either fall through or fall off. So, continuous functions are predictable. But what does that mean? Well, it means 2 big things. 1, no breaks. Well, we already know that breaks occur in functions when no limit exists there. Therefore, for a function to be continuous, it must have a limit at every x in its domain. Secondly, no holes. Continuous functions must be defined everywhere in their domain. Mathematically now, we say that continuous functions have this property. For every x equals c in their domain, the limit as x approaches c of f of x is equal to f of c. In other words, not only does the limit exist at every point, but the height the function reaches for every x matches the limit. How can you tell if this happens? It seems pretty complicated. It's actually easy. If you can evaluate any limit on f of x using only the substitution method, then the function is continuous. And that's all there is to it.
Okay. So, I'm going to go back and we're going to pick up that number 49. So, let's go back up to the top here. And let's come off to the side. Let's do number 49. Oh, let me look it up here. Number 49. Okay, so let me grab that. Okay, so now we got number 49 here. So, can we do direct substitution here? We can't, right? Because if you plugged in a -4 for x, the denominator would turn out to be 0. So that can't be done. So what can we do? Let me get a black. All right. Well, let's factor the denominator. You all remember you can factor the difference of two squares as conjugates. And now we can do this. Now can we substitute? We can, because that if you substitute in, then we have on top natural log of 2 over -8. And that would be your limit. Now you can actually do this on a calculator, but this is good. Okay, so that was number 49. All right, let's go back to where we were here. Yeah, so just talking again about an example. Again, if you have a function like the one shown here, as x approaches, the left-hand limit of this function as we approach 2 is 1. The right-hand limit, as we approach 2, it is 3, and they don't agree. So here we have the left-hand limit, the right-hand limit, they don't agree. Therefore, remember, you have to say the overall limit does not exist. So I think you all remember that. But so whenever left and right hand limits do not agree, we say the limit does not exist. Okay, then let's just go over an example of the 3 techniques we learned today. What's the limit of 3x minus 1 as x approaches 2? Here, always try substitution first. Does substitution work? Yep. 6 minus 1. Yeah, if you plug it in, 3 times 2 is 6 minus 1 is 5. Okay, so rejoice. You've got your limit, and you're done. Okay, here we have an example that has the difference of 2 cubes in it. Remember we talked about this last class? X cubed minus 8 over x minus 2. You can't substitute in 2 that you see over here on the left in your limit. That won't go, because that'll create a 0 in the denominator. So we go to factoring, and we now know how to factor such an item. Remember, you take first the cube root of x cubed minus the cube root of x cubed is x. The cube root of 8 is minus 2. That second factor is a trinomial. So you have a binomial and a trinomial. This first term here is this guy, x squared. -2 squared becomes this plus 4 on the end. And then in the middle, you have the product of the two. -2 times x is -2x, changes sign, plus 2x. That's how you factor that. And then, of course, look, the x minus 2's cancel. Now, can we do a substitution? Sure. We can plug in 2, and we get 4 plus 4 plus 4, or 12. Limits complete. And then just a reminder on conjugates. So I should have done this in a different color, but Yeah, let me just maybe do this over. So let me grab here, do a little. And then let's grab this. Ah, that's not correct. No, having a little trouble grabbing. So anyway, what? Yeah. So anyway, the conjugate of that numerator up there is, it's, let me change colors. It's the same thing you've got, changing the sign between, the sign of the binomial is the opposite. And of course, to make it legal, we have to multiply top and bottom by the same thing. And now on top, what happens when you multiply conjugates? And this is the beauty. You get the difference of two squares. So you get this x plus 4 square root squared, which is the thing without the square root sign, minus the other thing squared. And then look, x plus 4, x minus 4. Oh, that's just an x. In the bottom, yeah, that's a mess, but let it be. You'll find out things clear up real quickly. So you've got an x now up on the top, and the x cancels, and you're down to this expression right here. Whoops, 10. So you're down to this. And now I can substitute the square root of 8. I'm sorry, as x approaches 0, you have the square root of 4, which is 2 plus 2, so the denominator is 4. Answer, the limit is 1/4. Let's talk about a couple problems on the assignment. So this is one of them, number 44. Is the function ever discontinuous? And if so, where? And thirdly, what type of discontinuity is it? So when you take a look at this one, f of x equals 1 over x squared minus 4, what would create a discontinuity? A 0 in the denominator would be created if x was what? Either 2 or -2. And so those are the places. And then what type of discontinuity is that? That's going to give you asymptotes. Let's see, let's just quickly do that one. X over x squared minus 4. What is that? X squared minus 4. I lost it already. X over x squared minus 4. And you can see that at -2, we have one of these, we have an asymptote here, we have a negative, an infinite discontinuity. And over here at +2, we have another infinite. So that creates an infinite discontinuity. All right, let's go to this next one, number 49. Same question. Is the function ever discontinuous? If so, where? What type of discontinuity is it? So, what's going on here is we have an absolute value on the top. We have an x plus 7 on the bottom. You can see that let's see. So here, let's just graph that. Absolute value of x plus 7. And divided by x plus 7. You see what's going on there. We have a jump discontinuity. The left side never meets the right side. Okay? So, and where does it occur? At -7, because if you plug in a -7, you're going to get division by 0, which you can't have. All right? And then lastly, or maybe not lastly, but let's just take a look at this one, number 63. This is a different kind of a question. It says, what value of A makes the function continuous? This is one of those piecewise functions. What would cause this to be continuous? If the pieces came together, and that would mean when 3x squared equals ax minus 4. So you can find out by literally setting them equal and then going through the process of solving for a. I mean, if you solve for a, it's just a matter of algebra. But when a equals 4 over x plus 3x, that's so how can you find out when a piecewise function actually is continuous? When the two pieces meet, and the two pieces will meet when you set the two pieces equal to each other. You can find out what condition you need. Okay, and lastly, on what intervals is this function continuous? Number 77. Well, you maybe can't see it directly, but the one thing we got to watch out for is, could that denominator ever be 0? And if you want to find out when it happens, set it equal to 0 and solve. Okay, so in this case, x squared plus x plus 2 equals 0. Can we factor that? No, I don't think we're going to factor that. Well, let's see, plus, yeah, because if you did plus x plus 2 and x minus 1, but then, 2 times negative 1 would be negative 2, and it's a plus 2. So you can't factor that. So how could you solve this? You could use the quadratic, or you could complete the square. The quadratic, what? X equals minus b plus or minus square root b squared minus 4ac all over 2a. And you could go ahead and find out, hey, here are the points that would make that happen, and therefore that would make it discontinuous. So, are there any more questions from you? From class members? So let's get to the assignment. 2-4 down there on the bottom. And watch out, or not watch out, but this is the first time I think you've had a, what? Notice it says there are 2 optional ones there. So that means, yeah, I got to look at the book. What does that mean? 113, 115. Yeah, it just says you don't have to do those, but you might want to give it a try. Prove property 1 of theorem 2.1. Prove property 1 of theorem 2.2. So that you don't have to do those, but maybe you could give it a shot. Let me go back to the assignment. Anyone have a question? Thank you. Thank you for attending. Thank you for your question, Claire. All right, I guess that's it. Let's stop the broadcast.